Good afternoon, everyone. Today I have the great pleasure to welcome home, actually, Professor Marcelo Castier. Professor Castier is originally from Rio de Janeiro, Brazil. He obtained his bachelor and master degrees in chemical engineering from Federal University of Rio de Janeiro and his PhD degree from the Technical University of Denmark. He was an associate professor of chemical engineering at Federal University of Rio de Janeiro from 1988 to 2006 and was one of the founding members of the Atoms Group. Professor Castier is now affiliated with Universidad Paraguayo Alemana and Texas A&M University of Qatar. His scientific interests are focused on the development of thermodynamic models, new algorithms for computing thermodynamic equilibrium, application of thermodynamics to chemical process safety, energy integration, and the development of educational softwares. Professor Castier's interest in advanced computational applications has led to the development of ThermMath, a software for the automatic implementation of complex thermodynamic models. He is also the author of XSUS, a freely available educational software for chemical engineering thermodynamics. To date, he has published more than 80 times and has been cited more than 2,500 times. So once again, welcome back, Professor Castier. Thank you so much for being here, and please feel free to start your presentation.
First of all, thank you. Thanks for the introduction. It's a real pleasure to be here with you today. Coming home, yes, I was part of the Atoms history before it was called Atoms even, and it's a real pleasure to be back, even if virtually. So I'll start sharing my presentation, and just give me a second to do that. Yeah. And the topic I chose to speak about is on the volume-based equilibrium calculations, not necessarily because I think they are better than any other way of doing the calculation, just because almost by chance throughout my career, I started doing work that was related to this type of application. And then all of a sudden I had, of course, with collaborations, developed so many tools that they started to converge to some applications, and these are the applications that I'm going to talk about today. And I'll begin with, let's say, with the basics of why this type of calculation might be important. And I would begin with a tank. Suppose you have a storage tank, and you know the volume of this tank, you know the temperature of this tank, assuming that the temperature is uniform throughout the tank, and you know the component amounts. So how much of each component is inside the tank. And then you might be interested in trying to figure out many properties, calculate many properties. First of which, the number of phases. And I emphasize the number of phases because it will be important for the discussion of stability analysis in a few minutes. Then also I would like to know the amount of each phase, the composition of each phase, the volume of each phase, and I might be interested as well in calorimetric properties like the enthalpy of the phases, internal energies, and so forth. So this is the most kind of basic version of a volume-based calculation that might be of practical interest, but not only this one, where else it matters. For example, if you have a tank, but now this tank is leaking, so there is a leak from this tank. And in a situation such as this one, in addition to knowing the properties of the fluid within the tank, the same properties as we discussed before, the phase amounts, volumes, compositions, and so forth, you also want to know the same information for the fluid that's leaking from the tank. So if I want to do a kind of forecast of what might happen during an industrial accident, information is very important. I want to know the flow rate and the composition of what's leaking. So to do that, in addition to solving a flash TV and flash, I also need other properties such as the thermodynamic sound speed, and I need a flash with specifications of entropies, amounts, and stagnation enthalpy, and I'll come to that later on. Where else it matters? For example, it matters when I'm trying to do compositional grading, depending on the approach that I take. And again, if I think that I know the volume of my, say, reservoir, the temperature, assume it's isothermal, the component amounts within it, and I know the height of the reservoir, I can now account for the effect of gravity and calculate, again, the number of phases. It's, in principle, I know the phase volumes and the amounts in phase compositions as functions of height, as function of level, function of position. So in a problem such as this one, in which I have specifications of temperature, volume, and component amounts, what, say, basic thermodynamics tells us is that the equilibrium condition, the state of equilibrium, can be calculated by minimizing the Helmholtz energy compatible with the internal constraints of the system. Of course, the internal constraints play a role. If it's free, so there is no membrane, nothing, then it will just be a kind of phase equilibrium with specifications of TVN, and I can solve this problem by minimizing the Helmholtz energy. But the problem of minimizing the Helmholtz energy is normally solved assuming that there is a certain number of phases. And if you make the assumption that I have, say, 2 phases within the system, then I find out what distribution of the components and of the phase volumes will minimize the Helmholtz function. But it's not always the case that I know how many phases exist. In some cases, it's trivial. In some other cases, it's not. And then for many years now, say, phase equilibrium calculations embed the phase stability test. And in the case of the Helmholtz, and we can derive this phase stability test using different thermodynamic potentials. So the Michelson's work of 1981 used the Gibbs energy, but you can replicate that type of derivation using other potentials. So you can start with entropy or internal energy, or in the case here in terms of an expansion of the Helmholtz energy. So the problem is whether I can start, say, with a one-phase system and then split it in yellow phase and now a small amount of a green phase, but conserving the volume. So I now have a constraint that the volume of the original system and of the system after partition, these volumes have to be the same. And this leads to a formulation of the phase stability test based on the Helmholtz energy. If I have a way to minimize the Helmholtz energy and I have a phase stability test, regardless of the mathematical details of the implementation of each of them, I can start thinking about putting these things together, these elements together, and create some useful tool. As, for example, a flash algorithm that would minimize the Helmholtz energy, accounting for the possible inclusion or exclusion of phases. And the way these calculations, and now it's the traditional way of doing these sort of calculations, you start with a number of phases. I put here 1 because if you have a system with chemical equilibrium, you need to minimize the Helmholtz energy for a single phase chemical equilibrium. If you do not have, then you don't need to minimize the Helmholtz energy for one phase system because there is no alternative. But so either way, what happens next? So if you start with one phase, you test the stability of the system, the thermodynamic stability. If the system is unstable, so you add a phase to the system and you repeat the exercise of minimizing the Helmholtz energy. And when you do that, especially when you're doing calculations close to phase boundaries with systems with more than 3 phases, it's necessary to test for the possibility of eliminating a phase and this leading to a decrease in the thermodynamic potential. So normally we think about the phase equilibrium problem, minimization of Helmholtz energy, and the phase stability test, but there is a kind of a little brother here called phase elimination procedure that needs to be tested every now and then. So if we put these to work then, and we have very good and reliable numerical methods, I can solve a problem with specifications of temperature, volume, and phase amounts. So as we move through this presentation, my goal is not to go deep into details of the numerical implementations, but rather to highlight some points that would lead to the applications. The title had to do applications, and this will be my emphasis, not so much on the numerical details, but we can discuss them later on if there is any specific interest. So now on calculating phase stability based on the Helmholtz energy, so what you can do is basically replicate the way it was done by Michelson for the Gibbs energy in the 80s, and account for the fact that you need to have volume conservation. So remember, the volume of the single phase and the two-phase systems have to be the same. So you have to account for volume conservation. Then you have a phase stability function that is the difference of the chemical potential of the incipient phase, the trial phase, minus of the, say, the phase that's already present, times the amount in the incipient phase, but also you have this contribution that comes from the pressure difference. Now, regardless of the fact that you specify in T or T, V, and N, or T, P, and N, if a certain state is unstable, it's unstable, regardless of the specification you made. So in terms of identifying whether the system is stable or unstable, doing the way that is shown on this slide, or doing like Michelson did and proposed years ago, you get exactly the same answer. You have to. If you don't, it's because something is wrong. Because regardless of the specifications, if a system is unstable, it is unstable. So what is the point of doing the way I suggested is that the phase stability test in a flash calculation plays two roles. One is decide whether it's stable or unstable. This is the most obvious one. But then there's a bonus when you do this, which is to generate good initial estimates for the calculation with two phases. And if you have good initial estimates, you are sure that you are going to avoid trial solutions. Or sorry, not trial, non-trivial solutions. So you're going to avoid trivial solutions. So you'll get non-trivial solutions for sure. So this is the point of doing the way it was done. So the mathematics or the numerical trickery that has to be used in the phase stability test, I think, in my opinion, it's even more rigorous, or it's trickier than in the phase equilibrium calculation, because if you do the phase stability right, then you eliminate most of the problems you get from the second part, which is the minimization of the Helmholtz energies. So you need to ensure that you get the minimum, the global minimum of the phase stability function. This is easier said than done, because algorithms, minimization algorithms that give you certainty of attaining the global minimum are very costly from the computational viewpoint. So this is not how it was done here. It uses an empirical method, so it's called stochastic tunneling, combined with second order minimization. So there is no guarantee that we will always get the minimum, but there's a good probability that it does. So in this work, what I did was to compare with another algorithm that was published by Professor Firozabadi and his group. And I got near perfect agreement with his results. There is one discrepancy, and the discrepancy is that some of the results that he showed in his paper with his group also have not only transition from 1 to 2 phases, but also has from 2 to 3 phases. So his formulation was focusing on transition from 1 to 2, and when I did it, I did it in more general fashion. And for instance, these dotted lines here is the boundary between the two-phase is here and three-phase region. And this was done not by tracking the locus of these lines, the phase boundaries, but rather by creating a grid. The idea was to test the phase stability and the flash algorithm. So it was not, the idea was not to track this line, but to do thousands of flash calculations within a window of temperature and molar density. And by checking where we got stable or unstable system, and then draw this line. So a plot like this represents thousands and thousands of flash calculations, all of which converged based on this procedure. So this is one example with three phases. Here's another one that shows three phases. So I just picked up those that had 1 to 2 and 2 to 3 phases as outcome. Now, all of this started because of Rogério ESPOSITO, who was a PhD student with Frederico Tavares and myself around year 2000, 2005, this period, early 2000s. And he, at the time, worked for Petrobras, and as he still does, and he wanted to calculate compositional segregation. And then he became a very well-known specialist in this topic. But at that time, we wanted to do an isothermal calculation. And the way we did it as a TVN flash, and with the effect of gravity. And the way we approached, well, if you have a smooth transition as outcome of the effect of gravity, you need to integrate the value of dA over the whole region. This is essentially impossible to do analytically if you use any realistic or practical equation of state, so this has to be discretized, and this was the approach we took to create discrete layers and add the effect of each of these layers. And then there is the question, is there a vapor-liquid or a liquid-liquid interface? Oops, it was vapor-liquid, liquid-liquid. Mistake here. So that's what we wanted to find out. So we wrote the Helmholtz energy of each layer. We added the effect of gravity to the chemical potential, and we added the effects of all the layers to get an approximation to the Helmholtz energy of the whole system. And then we adopt a dual loop strategy. In an outer loop, we tried to locate the phase interface, and we used a very simple numerical method to do that, like simplex optimization, because we wanted to find out whether we had the vapor-liquid interface, say, at this level, or maybe at this level. And why positioning level interface is so important? It's very important because if the interface falls in the middle of a layer, then the density of this layer will give origin to a negative pressure, for example, and you have an unrealistic pressure profile. So positioning the interface exactly is of crucial importance. And the approach we took at that time was to have kind of two loops. In one loop, we locate the phase interface, and then we discretize, for example, here, we create discrete elements for the liquid, and we create discrete elements for the vapor, and we then use a TVN flash to find out the distribution of the elements within the phases. So, and then when we do this, the minimization, we need the terms of the gradient of the Hessian, and they were all done with analytical derivatives. And here are some examples that work that we did long ago. So these are the, say, pressure profile with depth. So here is depth, the vertical axis is the depth, and the horizontal is the pressure. So we have very small pressure change in the with depth in the gas phase, and then when we go across the interface and go into the liquid phase, then we get a much more pronounced pressure change. It looks like it's a straight line, which would be if the liquid were incompressible, but we didn't make this assumption here, just coming from the equation of state as it is. Here, so compositional profiles that we got at that time, so we could calculate the compositions of the liquid and vapor phase as function of position, of depth, and also in three-phase systems. Here we have a gas phase, an oil phase, and a water phase at the bottom. So we could calculate compositions, pressure profiles, everything based on this dual loop approach, numerical approach. And this is a calculation close to the critical point, and then you get this kind of smooth transition. This is height against density, smooth transition of density close to the critical point temperature. Now, we had this tool, and there was a paper appeared in Chemical Engineering Science by a group in Shell Research, in which they did molecular simulations of gas centrifugation. So the idea was to purify natural gas using centrifugation, and they did molecular simulations. And Fred and I said, oh, okay, we can do it with our program. Let's do it. And we got the results in like 3 days. And so what did we do? So we had a vertical cylinder. Now we have a horizontal cylinder. What changes from one calculation to the other is how the effect of the external field, now a centrifugal field, affects the chemical potential. And off we go using exactly the same idea, exactly the same approach. And the results we got were nearly perfect match with the results of molecular simulation from the Shell Research group. And here, what we see is a pressure as a function of the rotation axis at 70,000 RPM. This is a mixture of argon and ethane. And here we see a point where there is a phase transition, then there is a sudden change in slope of the pressure. The pressure increases much more rapidly because it's a liquid phase from this point and onwards. And we could get composition profiles. So the basic idea of using ultracentrifugation was that you could, in the outer layer away from the rotation axis, you could enrich, get enrichment of the heaviest components, which in this case would be hydrogen sulfide and carbon dioxide, and this is exactly what you see here. So this was a kind of immediate application of the work of Rogério ESPOSITO by just switching from a vertical to a horizontal geometry. And then we got excited, and we decided to go beyond hydrocarbons and play with colloidal particles, very small particles of called percol. Percol is used in biomedical separations, and it's small particles of silica coated with a polymer. And when you run a percol gradient, what you do it to separate different parts of cells, organelles. And here, I think this picture, I just took this picture as an illustration. I think these bands here are something of color just to show how, depending on the density, the particles get together. They are separated essentially based on density. So we formulated this. Now, this time, we use an equation of state for spherocylinders, developed by Professor Silvio Canuto of the University of São Paulo. He had just developed this equation of state. We used this one, and it's similar to the problem that for the centrifugation, with this important difference is that we made this calculation assuming we had the Macmillan-Myers system, in which our assumption is that we had a wall permeable to the fluid, to the solvent, in such a way that it had a field of the solvent, and then the solutes were modeled within by means of the equation of state. And because of that, then we had to use an effective mass for the particles, which was the mass of the particle minus the particle of sorry, minus the mass of the solvent that would be occupying the same volume, basically buoyancy. And then off we went with these calculations, and these are comparisons of the results from this sort of TVN flash with, again, Monte Carlo simulations. The results for hard spheres here. The results are essentially identical with exceptions at the edges because of edge effects on the Monte Carlo simulation. But in the bulk of the system, the match is essentially perfect. And this sort of bending that occurs in experiments, here we did a simulation. These is particle numbers against distance from the rotation axis. And here is the particle number of the Perkol particles, the particles that form the gradient. And here are different particles with slightly different densities and how they would create peaks. And that's exactly what we see. Now, we cannot compare quantitative. This is just a picture that I took yesterday when preparing, so there is no quantitative comparison, but there's a qualitative comparison that you get peaks according to density. And the least dense particles, the spread is larger. They become more focused, narrower distribution as the particles become heavier. Everything just makes sense. Now, this program was used for many years, and then in 2016, it became so complicated to make changes because so many people had worked on it, including myself, and it was really difficult that we decided to have a new beginning in 2016. So we wrote an entirely new code for volume-based calculations, allowing for multiple regions. So I have, for instance, I have a pore or porous materials, and I have a pore size distribution. I can say pore of type A is a region, pore of type B is a region. And so I can have this sort of flexibility with dynamic memory allocation for different regions, different components, any number of external fields, more than one field in a given direction, and fields in perpendicular directions as well. And we were megalomaniac at that time, and we called the program Mega TVN, the name by which it goes to this day, even though reality has shown that it's not so powerful as it was originally intended, but the name remained. So first work with this was with Professor Yannis Economo and two Master of Science students. And so this was kind of a picture of what we had in mind, the ability to, say, have as for example here, let's say the white region is a bulk fluid, and then I have a green pore, and I have a red pore, and I have three regions, and the program can handle them all, including the possibility of having a, say, gravity along with the effect of an external wall. And we can account in this development, we account for replicas. So we have, again, a pore size distribution. I have a certain pore, and I have, say, 10 to the power 6 of that pore, and then another pore, I have 10 to the power 5. So I have a different population of pores. All of this is accounted for, all these possibilities. But again, is the idea of adding the contributions of discrete layers of the Helmholtz, discrete contributions of the Helmholtz function over layers and now over regions. In our work, we used Peng-Robinson volume translation, and we considered two types of fluid wall interactions and gravity. And just, this is not actually what the program is meant for. It's not meant to be a replacement for molecular simulation, absolutely not. There are several limitations and severe limitations to doing that, but this kind of gives the qualitative idea of what the type of result we get. So it gets an internal profile within the pore. And again, not meant to be a quantitative comparison, but it kind of gives the right trend, points in the right direction. Now, what it meant for is to compare macroscopic properties. And here this slide compares the results of this program with density function theory results from Professor Firozabadi and his group. And the agreement is very, very good. This is a very fair comparison in the sense that we use the same model 10 grams with volume translation and the same fluid wall interaction potential, which in this case, I don't remember, but I think it was the still potential. And just for the sake of illustration, in this calculation we did, in this particular plot is a result in which we used fluid wall interactions, we used gravity. So we had two fields acting on the system at the same time in perpendicular directions. And here is the molar concentration profile of methane in CO2 as a function of depth. And here is, again, not meant for quantitative comparison, but for qualitative comparisons only. Here is the internal profile, internal mole fraction of CO2 within the pore as a function of distance from the wall at two different depths. So here we see the effect of depth and height, depth and confinement together at the same time. More recently, we extended this work using the Saft-Jahmy equation of state, and we have made comparisons with systems in which we took into account pore size distribution, so the ability of taking into account several regions. And here is just an example of what we get for the absorption of CO2 on activated carbon compared to experimental data. Now, let me move on to applications to process safety. And process safety is a very broad subject, very interesting, that goes all the way from applied psychology to try to understand why people take safe or unsafe actions at the workplace and in their daily lives, but also includes very technical subjects. And in particular, I have been working with Professor Luc VÉCHOT from Texas A&M University for a number of years on fluid releases from pressurized vessels. And there are two situations. You may intend to do that if you are opening a relief valve. So you have an overpressure and you want to open the valve to the vessel to relieve the pressure, or that it may be an accident, an industrial accident. Either way, trying to understand what happens when there is a fluid release from pressurized vessel is a very, very interesting problem of practical importance. Now, what I'm going to show you are some results and kind of somehow the Lego bricks that went together into the simulation of venting and leaks from reactive and non-reactive systems. And the first thing that's not necessarily easy or obvious is to find out what phase is leaking. And my drawing skills are terrible. I'm sorry for that, but I think this image still conveys the message. So suppose yellow is liquid and white is vapor. And let's say at the beginning of a leak, you have a leak from the liquid phase, in this case, and then as material leaves the vessel, there will be an interval of time in which you have leak from both phases at the same time, and after a longer period of time, the leak will be from the vapor phase. And this has a dramatic impact on the composition of what's leaking and the flow rate of what's leaking. Well, in a vertical cylinder, it's very easy. There is a relationship between volume of liquid and level is very simple, because the volume is the area of the basis times the height. Not so easy when you have a, say, horizontal cylinder, because the cross sectional area changes as the level changes, or when you have a horizontal cylinder with hemispherical or toroidal caps. So the relationship between volume and height is not that trivial. In some cases, you need to do even numerical calculations. If you have the volume, you want to have the height, you need to do some trial and error, some Newton-Raphson calculation to find it out. It's not necessarily trivial. Anyway, here, what we did was first to formulate a mass energy balance for a leaking tank. And let's think that the green streams are, say, the normal operating streams, one feed and two normal outputs, and then there is a leak, which is the red output. Well, I need to do a mass balance on a molar basis, so it's flow in minus flow out. And if I have reactions in the system, there is a reason for why this is very important or very useful. Now I need to account for the rate of reaction. So I need to write a molar mass balance for each component, a differential balance, and an energy balance, again, accounting for the enthalpies of the streams coming in and the enthalpies of the stream going out, and eventually some heat load. And specifically here, I put the kinetic energy term in the outstreams because they may be very important, not so much so for the regular streams, but for the accidental leak, it's very important, as I will comment later on. Now, again, what I need to do is to integrate a set of differential equations. I cannot do this analytically for the most practical cases, but the integration will give me at each moment in time the values of the internal energy, the component amount, and the volume is fixed. So I know U, V, and N. So if I assume that the properties within the tank are uniform, I have to solve a U, V, N flash, a flash that requires entropy maximization. I'm not going into the details of this calculation, but this was something that I worked on in 2008, 2009, and this came out as a publication, Fluid Phase Equilibrium. Another thing that I need to worry about is the leak flow rate. And the way it was modeled in this conventional model is to assume that the leaking point is at steady state, and it is a converging nozzle, converging adiabatic and isentropic nozzle. And if this is the case, then the enthalpy of the fluid inside the tank has to be equal to the enthalpy of the fluid that leaves the tank plus the kinetic energy. And assume it's isentropic, then I have a problem in which I have an enthalpy specification, I have an entropy specification, and this is a flash with specified values of stagnation enthalpy, which is summation enthalpy plus kinetic energy, stagnation enthalpy, entropy, and component amount is an HS flash. Because we had that problem, then we set out to develop an algorithm to do that. And just to, again, I'm not going to discuss the details of the algorithm, but I may have two situations here. I may have a subsonic flow, or I can have a sonic flow. So this is energy balance, this is entropy, mechanical equilibrium, this is phase equilibrium, equal chemical potentials. And if I have a sonic flow, now the kinetic energy would depend, of the output stream depends on the sound speed. And the output flow may not have just one phase, it may have more than one phase. So this throws the need for another algorithm, which is an algorithm to calculate sound speed in systems that have more than one phase. So it is like a chain of things that you need to put together to simulate a leak from a tank, such as those that we are trying to do. So off we go, and to calculate sound speed in multi-phase systems. In a single phase system, what you need to do is to calculate the change of pressure with density at constant entropy. But in a multi-phase systems, the volume is the summation of phase volumes, the entropy is the summation of the phase entropies, and the amounts are the summation of the phase amounts. And this creates a huge chain of manipulations that you have to carry out in order to calculate these derivatives. So it takes quite a few pages to show the equations that need to be solved, but it can be done, and it works pretty well. It's very interesting. And the interesting things is that the sound speed may have kind of some of these abrupt changes, and the algorithms capture this very well. And these changes are the outcome of the fact that the compressibility of the system changes dramatically when there is or there is not a vapor phase in the system. So here are just some illustrations of this fact. Now, all of this had to be put together, UVN flash, HSN flash, sound speed calculations for multi-phase systems. And when you have all of this together, then we can go back to the fluid releases from pressurized vessels. And here are some results. This is just air. So there is just one phase, air, release of air from tanks. The simulations are the solid lines, and the dotted lines are the results of experiments. Here is a rather complicated calculations based on an industrial accident happening in Italy, called Via Reggio accident, in which a train wagon capsized and leaked. And of course, because it was an accident, there is no experimental data as such for the accident, but other people tried to model this, and we compared our results to their results with excellent agreement. And we calculate how the temperature, how the pressure changed over time during the leak. And the leak was initially from a liquid phase within the tank, and then afterwards, because the liquid level was lowered, and then at the end, it was from the vapor phase. Here, what I show you is time against flow rates. So here, for example, take this line, the flow rate of each component as it leaks from the system. So here it's leaking from the from the liquid phase. So the flow rates, they decrease, but not dramatically. And then at this point in time, then it becomes a leak from the vapor phase, and then the depressurization takes place very rapidly, and the flow rates decrease by orders of magnitude very rapidly. So all of these we could kind of simulate with our program of our process safety simulator. Now, I mentioned that reactive systems were very important. The reason why they are very important is because certain materials, and this is peroxide, DTBP, diethyl peroxide, these is used as in polymerizations, and these substances are very tricky, because you may leave them and almost nothing will apparently happen, but this reaction here that forms acetone and ethane is an exothermic reaction. So if this decomposition starts, then you produce, your products are much more volatile than DTBP, and the temperature increases. So if it's not controlled, this is what you experience in your vessel. So an exponential increase of temperature and of pressure. Here is the pressure curve. And very easily you can have an industrial accident if you don't take action. So this simulation here was compared to experimental data, very nearly perfect agreement. And here is a simulation of what happens when you have a relief valve in your system. So the relief valve opens, and the moment the relief valve opens, so here we have examples of 3 situations opening at 0.4 megapascal, 0.45, and 0.5. And then if you have a valve of the correct size, then you kill the reaction. So essentially you kill the reaction because you discharge the reactor completely. Now, if the valve, the relief is not designed properly, you may have a situation in which it decreases, then it increases again. So that's why it's important to get it right. Now, this, if you look at this curve here, it looks as if it's just killing and just kind of vertical line down. Here we have magnified, this is temperature, not pressure, but temperature just a few seconds after the opening of the valve. And I have no way of telling whether this actually happens or not. But in terms of kind of the intricacies of the calculation, it's fascinating because here, the first leg, you have two-phase flow, and here it's wrong, it's one phase. And then this point of minimum up to here, it's one phase flow. And at this point, there's a transition from sonic to subsonic flow. So very complex behavior here. Again, I have no way of telling whether this actually happens or not. Probably, I would say probably not, because in real life in an accident, this is a very messy situation. It's not as well behaved as the assumptions we have made, but we had to make assumptions to move on. Now, final set of examples, it has to do with supersonic separators. And because we had all these tools that I mentioned together, we could go into the simulation of supersonic separators. What are they? They are piece of equipment in which, say, you have a feed from the left, so it's a gas, and it goes into a conversion nozzle, and then as it reaches the throat, if the conditions are right, it should be at sonic speed, and then as it expands into the diversion section, it becomes supersonic, and because the kinetic energy increases so much, the entropy has to go down because of energy conservation, and this causes a decrease in temperature and partial condensation if you have, say, a contaminated natural gas. So the heaviest components will typically condense, and you can design a kind of output to collect the liquid, and you have a purified gas at the exit. So the claimed advantage of the people who design and sell these things is that they are compact and they're useful for inclusion in platforms. Petrobras, for instance, has an interest in this type of device. Now, if you want to analyze this device, I put the equation here, but no worries, I'm not going into the details. You need to analyze first, to take some kind of big look at what's going on. And here what I have is, this is mass balance, these are enthalpy balances, this is entropy. And you need to do this section by section between the entrance and the throat, and then between the throat and a side stream, the position where you have a side stream to remove liquid. And then inside this equipment, you normally have a shock wave, so you need to model the shock wave. The shock wave is not isentropic, and then after the shock wave, so at the shock wave, you need to use the momentum balance, and then after the shock wave, it's isentropic again. So you have HSN flashes throughout, almost throughout the whole piece of equipment. So it's a playground for HSN flash calculations. Now, the way I initially did it, the first work of the series was to take the length of the device and discretize it the way we discretized compositional grading and the effect of gravity or centrifugation. So just create discrete elements and get the profiles. And these are the results of the dotted line here and of the blue curve. So these are the results of kind of slicing the device horizontally and solving these equations point by point. Now, if you have a piece of equipment like this in a process simulator, say you want to add this to Aspen, for example, you don't care necessarily about the internal profiles. perhaps at the end, but not in the middle of the calculation. So what we set out to do more recently was to modify our procedure and just calculate the key points that are necessary to get the output conditions. And these key points are the condition at the throat, then the conditions at the shock wave, and the conditions at the exit. So by doing this, we could save a lot of computed time. So here are examples. This example has no side stream. This example is the effect of the side stream location on the conditions of the outputs. So we could do a lot of things much, much quicker than we could do before. So just examples of this is Mach number, sound speed of sound inside, so the fluid velocity as divided by the sound velocity at each given position. And here, just a composition, how the composition changes between the feed and the gas that comes out for a given situation. Now, approaching the end, so what is my current work? I'm working with Frederico Tavares and a student, Tulio Freire, on phase behavior of fluids confined within small geological formations. I'm working with Luis Franco from Unicamp and André Gonçalves, PhD students, on the behavior of confined fluids under the effect of gravity, revisiting that problem and going deeper into it with some kind of deep questions, at least to us, as to kind of trying to understand several things. We are working on liquid swelling inside these tanks and these process safety calculations. When you have, so the tank opens, there is bubble formation, and the liquid kind of rises because it's liquid plus gas inside the phase. So this has an impact on the rates of the releases. We are modeling this. We have a student just defended a thesis last week. We gave a kind of partial answer. We're not entirely happy. We expect to do some progress in the coming months, and we are working on uncertainty in the design, effect of uncertainty on the design of supersonic separators. So these are topics that are somehow related to what I presented. In addition to those, I'm working on the simulation of pressure retarded osmosis, a technique to recover mechanical power from desalination plants, and it's an application of equations of state for electrolyte solutions. Also, I'm collaborating on an European project on the development and application of equations of state for electrolyte solutions, and I'm working on the modeling of separation units for the production of cannabis derivatives. The people. Now, quite often we see presentations with a picture of everyone of a group. Now, what I presented here is the outcome of more than 20 years of work, and it's just impossible to mention everyone. What I would like to say is that I remember each and every one of those projects and of the people that worked on them, and I'm sincerely grateful for their collaboration, which was essential to accomplish what was shown here today. Some final and random thoughts on the challenge of using complex models for the applications I have shown. And I would like to illustrate these with what I call the IKEA syndrome. IKEA sells furniture, and you go to the shop and you see this, let's say this piece of furniture, and it is useful, it is practical, it works well for what I need, and I want it. And I buy, it comes, I take it home in a box, and then I'm faced with this, with the challenging of put it all together. And when I come to this point, then I need to think, do I really want it? Now, if we look at this plot, beautiful representation of the volumetric independence of hydrocarbons from the work of Lafitte et al. And it's useful, it's practical, it works well, and I want it until I take the paper from Lafitte et al. And these are part of the equations, probably at least an equal amount of equations, if not twice as much, to accomplish, to implement that. And then I ask myself, do I really want it? Now, in all fairness, I am guilty as charged. If I look back, my own papers mostly fail at presenting information in a easy to use way. So I am not doing better than anyone else. And in fact, it's the example I took from the paper of Saft Yami is to a large extent unfair because they did an excellent job of trying to make life easier because they have an appendix with all the equations that are necessary to model it, but not necessarily in the way to use. So everyone, and I have talked to many people who have implemented SAP-YAMI, still it takes a lot of time to navigate through the jungle of formulas. Complexity will not go away. We model complex phenomena. We should not expect our equations to be simple. They will not be simple. They will not be simple. What we need to do, I think, is to make a better job at communicating what our model is. And I think we do a pretty good job, mostly, in terms of presenting the model so that people can understand how the model is built or the logic. I think it's great, but I think there should be ways, maybe these, nowadays there are these papers in which you can add something like supplementary material, like a guideline, step by step, how to implement these very complex models. I think these would be very useful. So I know I have an editor of fluid physics Libra here in the audience, and I think this should be something that we, here is a suggestion. My personal workflow for a number of years, I try to understand the model to the best of my ability. I try to understand how to program the model, but for many years, I have not programmed models myself. I just use computer algebra to do that. And I think that if you know how to use computer algebra, especially for the young people, so if you spend some time learning how to use Mathematica well, Maple well, it pays off. It's an investment, initial investment of time, but it will make your life much easier further down the road. Finally, invitation to visit my channel. I have a channel on YouTube called Geothermal Channel with educational material, some interviews, some videos of experiments. So here is an invitation if you to visit this channel online. And with that, I end my presentation. Thank you very much again for the invitation, and thank you very much for attending my presentation. Thank you all.
Thank you so much, Professor Castier, for your presentation. It's always a pleasure to have you here. And we're now open for questions. If you want to ask one, please feel free to enable your microphone or write it down in the chat so we can read it. Our YouTube viewers can also ask questions, of course. Who wants to be the first?
Yanis.
Please, Professor Economo, go ahead.
Good. So let me start by thanking Marcelo for giving an excellent talk. I should point out publicly that I miss Marcelo a lot since he left Doha. We collaborated on many fascinating projects and we had excellent discussions. And I would like to point out for the young generation here that Professor Castier is the only person I know that continues to be so fascinated about computer algebra and developing equations of state. So during our time together, whenever we had a problem, we would go to Marcelo because we knew that he would provide a solution and an explanation. So Marcelo, congratulations for the excellent work and for continuing collaborating with us in Texas A&M at Qatar. So
Thank you thank you, Yanis.
I have a general question. I mean, over these years that we collaborate together and before and after, you solve a lot of problems which have immediate practical application. So for example, if I am an engineer working on a process safety, I would go immediately and look for a solution with Aspen or with Pro 2 or with any other package. Can you explain us a little bit what are maybe the limitations in a process simulator with respect to this very different flash type of algorithm? Because the majority of flash algorithms have to do with TP flash. So if someone wants to do a calculation using one of the commercial simulators, what will he get?
Yeah. So let me try to break down my answer in two parts. First, so if you take the origins of Aspen and other programs that existed before Aspen, they were originally designed for steady state simulations. And in steady state simulations, it's the typical case you want to calculate equilibrium is with specifications of temperature and pressure, and the volume comes as as an afterthought. Okay, I have these flashes, this temperature and pressure, and I have these phase densities. Then, well, I need a tank that will have, let's say, I want to have a residence time of say 3 minutes, 4 minutes. I know the amount, the phase densities, and I calculate the volume as an afterthought. And this is absolutely okay. No problem with that. These issues with, or these calculations with volume, they come very naturally into play when you are trying to do some dynamic simulation. Because in a dynamic simulation, you typically assume that you have the vessel, so it has a volume, and then the pressure will fluctuate within the vessel. And you can model it with several levels of approximation. You can make a very detailed, like CFD-like model in which you know the internal distribution of pressure density depending on the geometry of what's coming in and the point of entrance and point of exit. But these simulations take very long. They are very detailed, very nice, but they take long time. So I think what I presented here fits somewhere in between. It's definitely not as detailed as CFD, but it's much quicker. And it's not really meant for steady state simulation. It's much more geared towards dynamic simulations under the assumption that you have homogeneous systems inside. So you have a homogeneous system. So if you want, now there are tools for dynamic simulation. So even Aspen has, and then you have other professional software that do these calculations. And maybe they would, honestly, I haven't run them myself. If someone has and would like to make a comment, I would be interested in learning about them, but I haven't run these programs myself. But I pretty much like to be in control. This is good and bad at some points, but I like to be in control and develop my own things and understand exactly what's inside. So that's why these problems caught my attention, and because they put together, so these process safety applications, I love them because they put together so much knowledge about phase equilibrium calculations. So many things have to come together to make these calculations work as I shown. And honestly, this came almost by coincidence, because I got interested in these problems even before realizing that I needed all of them for the process safety applications. So process safety came as almost as an accident, if you will. because of my collaboration with Professor Luc VÉCHOT, friend Luc VÉCHOT.
Thank you.
There's a question from a YouTube viewer. Andres Porras asks, and he says, "Thank you for your presentation, Professor Castier. When you run the stability tests, do you consider the possibility of stable solid phases formation into the systems?"
No, because in the examples I have shown, I knew that this would not happen. So I was away from this condition, with one exception in the set of results that I discussed, which was in the centrifugation of natural gas, and there I had CO2 at a condition where it might happen. And then in that one, we included the possibility of solid CO2 formation in the phase stability test, but it turned out that it did not happen. But this was accounted for. But generally speaking, I don't. And normally the problems of interest are normally away from this condition. It might be a good idea to do that for the supersonic separator, because there it may be an issue. Definitely can be an issue. This is, yeah, this is a very good point. And thanks for asking. Generally speaking, no. One exception, centrifugation case that I discussed, but as a general rule, it would be a good thing to have in the supersonic separator. Good points. Thanks for calling my attention to that.
All right. Would anyone else like to ask a question?
No, just a comment. Marcelo, thank you for the presentation. I think it was lovely. I think everybody enjoyed a lot. Just a comment about this question. I don't think it's a big deal to include a solid phase, especially if it's a pure phase. I think the point is, when you include a solid phase, you have to ask if the kinetic plays an important role or not. Because in this calculation, you neglected the kinetic effect. You suppose that the nucleation is fast enough to be neglected. But in solid phase, maybe if you appear solid phase, maybe you cannot do that. Just that, yeah, maybe.
Mm-hmm. Exactly. Yeah. But on the issue of the stability, including the stability of solid phases, there was a piece of work that I did with a student from Brazil, which was on the precipitation of salts, salt precipitation. There, the kinetics is quick, and the problem there is that suppose you have many ions in solution, some cations, some anions, and you change the conditions, and you want to find out which salt or which salts will precipitate, and you have all possible combinations of cations and anions and hydrated species, because some of the salts will precipitate as hydrated species, and you have all these possibilities, and you need to find out which one or which ones will actually go into the solid phase. It's a very nice application of phase stability with very the nature of the problem. If you assume that the salts precipitated, each of them will precipitate as a pure phase, is very allows for very interesting simplifications. So it's beautiful problem, beautiful problem. And I had the pleasure of working on that, and probably I'll work on that again, because with Yanis in the project we are working on the European project we are working on, one of the ultimate goals is to calculate solid liquid equilibrium with electrolyte systems. So I think we are going back to this problem.
Interesting. Can you comment more about your comparison between DFT and local minimum of free energy? Because we know that you can do DFT instead of calculate the way you're doing. But, well, as you have very well no expertise on this complex minimization, the natural way to do is using your knowledge already. But I wonder if maybe the time consumed to do DFT is about the same as the time consumed to do this calculation, because you need to discretize your box, and maybe the number of this discretization is the amount the amount of calculation you need to do correctly. Maybe is close the order of magnitude as in DFT, I think. But I want to comment about this.
Okay. So I have never run a DFT code myself, but we had a student together with Leonardo Travalloni, Gabriel Barbosa, who did both, and who did DFT, and for the same problem, they run at about the same time, depending. So when you do these discretizations that I showed, then it's like you're solving. So if you have 100 discrete layers, it's as if you're solving a problem, a flash problem with 100 phases. So it's a kind of large problem, and it takes time. So I don't know, for a mixture of like 4 or 5 components with 100 layers, it might take a minute or two in a computer, and this is about the time the DFT calculation might take. Now, having said that, I'm working with Luis Franco and André Gonçalves, as I mentioned, on these calculations, and they were kind of not sleepy because Ahmed Ali Yazidi and Yanis, we worked with implementing SAFT VRME, but now we are going in another direction with Luis Franco and André. And when we are trying to couple these with phase stability tests, and then there are several questions that are kind of very difficult to answer, and we don't know the answer, I would say. Luis may intervene if you want. But first, one of the things is that we have been asking ourselves is what is pore condensation? Because if you think about what goes on within a pore, is the moment you have an attractive wall and you put some solute within that pore, it will go close to the wall, and you have a very high density region inside the pore anyway. So if you want to call it solid because it's very ordered, because it's close to the wall, or you can call it solid, or if you want to call it liquid, but you have a region of very high density within the pore from the outset. So, and then there is the issue of the scale. So if you are doing confinement and you want to do as we have been doing with this multipotential theory of adsorption, you are inheriting the structure of a bulk phase and forcing it inside a pore of nanometric size. And this is definitely not a theory, not grounded on theory. And that's why I mentioned that if you look at the profiles inside the pore, these are not to be trusted as a quantitative result because they are constrained by the structure of the fluid in a bulk liquid that you are imposing within the pore without making any change to that structure. On that note, I think that the work that we did with Leonardo Travoloni is very interesting because we, even if empirically, we tried to incorporate the change in the structure that the fluid experience, the molecules experience because of confinement, we tried to include them incorporate them into the equation of state. So the equation of state gets modified because of the effect of confinement. So this is very kind of comfortable to think of, say, multipotential theory of adsorption as like a supermarket where you pick up an equation of state and you pick up a fluid wall interaction, you put them together and you get results, and you do get results. But these results are not really grounded on theory. They may work, they may get a good agreement with experimental data, they may give a good agreement with DFT, but they have a serious theoretical limitation. One thing that we have been discussing, we haven't done yet, is to try to modify the fluid wall interaction and try to think of an try to get a corresponding free energy, but we haven't done anything yet on that. This is kind of an idea floating around. For practical applications, I would say, Yannis mentioned that I do think that may have practical implications right away or in a short period of time. I think if I had to do something that would take into account gravity confinement at the same time, what my way of doing right now with the tools that I have, not the tools that exist because I don't necessarily know of all of them, but with the tools I have, I would just pick up one of the equations that Leonardo and Gabriel Barbosa developed for confined fluids, in which we embed the effect of confinement within the equation and put gravity as an external effect. I wouldn't necessarily do as taking a still potential with gravity and getting the results. We did that with NUR. I showed the results. It's interesting. It's qualitatively interesting, but not necessarily sound in terms of theory, or we may not give the right results.
Thanks, Marcelo. Another question is, one approach that may be very interesting in use classical or semi-classical thermodynamic case, maybe include the swelling or contraction or expansion of the solid phase. We see several these new materials that may change this pore size during the adsorption. Do you think that it may be possible using your approach with free energy calculation directly?
I'm not sure. So I don't know. The answer is I don't know.
Suppose that you have a model for the structure of the soil. So you have a kind of free energy of the solid phase. Maybe it will be another only piece of free energy to minimize together. I don't know. I'm just thinking now. I'm not elaborating this further or before, but I'm just thinking now, because we do have some free energy modeling for some structure, but it's not clear how to use using DFT, for example. I think Chapman did that once. Chapman published last year or 2 years ago something using DFT and also a kind of modeling for structure of the solid phase. So I just wonder if you thought about this.
Well, well. No, we see in our, I think it was our latest work with Gabriel Barbosa. We did something roughly in this direction, and why and how? Because in work with Panagiotis Krokidas and Yanis and others, we did some simulations of ZIFs, zeolitic imidazolate frameworks, and we saw that in these ZIFs, these structures vibrate a lot, and the pore size changes as molecules approach and go across and then exit, say, from the other side, let's say this way. So the structures respond to the effect of temperature, and they respond to the effect of proximity of the penetrating molecule. And we could quantify, by doing molecular dynamics, we could quantify several of these effects, of course, based on molecular dynamics results. So what we did with Gabriel was to impose a, say, pore size distribution, and then do calculations using pore size, trying to figure out what the pore size distribution would be, and then we could, to some extent,
but without any model for the solid phase.
Without any model for the solid, just kind of treating, treating this pore size distribution as a kind of fitting parameter, but without any model for the solid, absolutely, without any model for the solid. The issue here, so if you just want to use this TVN thing, the problem with this is that the volume would not be constant anymore. So probably would need to use a different thermodynamic potential to respond to the change of volume of the system. But I don't think it would work with a Helmholtz minimization. At least I don't see how to do it right now. You thought about it, right? You thought about the question right now. I'm just thinking about the answer right now. So I may be talking nonsense, but so this is a risk I must take.
Okay, yeah, sure. Thanks.
Good to be at home because you are free to talk nonsense.
Yeah, sure.
I think Professor Raja has a question. Please go ahead.
Thank you, Marcelo, for your enlightening talk. Just one clarification, how do you take into account solubility of inert gases, like say oxygen, for example? Can you calculate gas-liquid equilibrium as well in your TBN system, or does it make any difference?
Yeah, first of all, Raja, thank you very much for being here. To those who do not know me, Professor Raja Gopal was my supervisor in my Master's of Science. I learned a lot from him. I owe him a lot. So I'm very happy that you are here and you're asking a question. In all these calculations, Raja, that I showed in all regards on the process safety and on the other type of calculation, in all of them I used the equations of states. So I never used like symmetric or unsymmetric active coefficients. In all of them, it was with equations of state. And then One may ask on the accuracy of the equation of state for a specific application. And in many of these cases, I was not really concerned about the accuracy of the specific representation of a given system, but rather on the putting together a procedure that would work. So in many of these, for instance, in most of these calculations that I showed, I just used Penn-Robinson or Penn-Robinson with volume translation with KIJs, many cases, in some others where they were not readily available without them. So on the accuracy of many of these results, they might be questionable, because the goal was to develop an algorithm that would work at, say, high pressure, and kind of made the point that it worked. But specifically regarding the solubility of light components, I just treated everything as an equation of state. In all the examples, from the first to the end, it was always with equation of state. And then it's just one more component. One thing that perhaps I should mention, kind of numerical detail, is that in many cases, especially when you're trying to build profiles within these pores, or when you are dealing with this solubilities that are very small, of the order of 10 to the minus 10, 10 to the minus 15 in mole fractions or more, or less. Then in many of these algorithms that I showed, there is an automatic trigger that if the concentration falls below, or the mole fraction falls below a certain range, then that component is switched off. So if let's say if it's oxygen, solubility of oxygen in liquid, and it goes beyond during the course of the iterations, falls below a certain range, then I switch off and say, okay, oxygen, for the sake of an example, is absent from the liquid phase and all of it from the vapor phase. So this is an approximation, which is convenient because it decreases the size of the problem. Now I have, say, a few unknowns less to find out, because I have decided that all the oxygen is in the vapor or in the gas phase, and there is no oxygen in the liquid phase. So this switch is present in almost all the programs that I showed here. They have this switch to simplify things and avoid numerical problems that often arise when you have a component that is in tiny amount as compared to the presence of some others. I don't know whether I have answered your question, Raja.
No, it's you answered very well. Because I worried about oxygen, nitrogen, and hydrogen cyanide. At high pressures, would you lose Henry's law or equilibrium liquid vapor? This is what basically what type of. They seem to disagree very. For example, if you use one case, there may be three phases. You use another case, there may be not be even three phases. It varies very much at higher pressures. This is what I was wondering about.
Mm-hmm. Yeah.
The other problem you're talking about is also very important. You talked about bubbles and formation. You are working currently, you are telling me. There again, there's a problem of variation in surface tension with pressure. It can cause high pressures when the bubble breaks. So I was wondering, the bubbles also be part of the liquid, as you were mentioning.
Yeah, so yeah, these I would qualify as a work in progress. But so what we did, I didn't show any result of this, but what we did, there is a set of guidelines from DAWASS, which is Design Institute for Relief Systems. I do not know what, emergency relief systems. So DAWASS is an institution that is worried about the design of emergency relief systems, and they have a set of guidelines, a set of equations to size the vents for emergency relief. And these guidelines, they are based on the values of surface tension and viscosity. And what we did was to implement the Dyer's equation into the Dyer's recommended equations into our simulator. And then we had to calculate surface tension, and we had to calculate viscosities. And for what we wanted to do, to have, was a model for viscosity, for example, that did not request much specific information about the systems, because one of the cases of interest is the composition of peroxides, this reaction that I showed. Luc VÉCHOT worked with this. He likes these systems very much, kind of from the scientific viewpoint. Of course, they are dangerous, but but there's not much information about the properties of peroxides to the level that some models would require. So we made a choice for a method developed by Professor Teja. It's like a corresponding states method. You get decent results. And then for surface tension, we use the paracore model. And then, this is where things get kind of very interesting and tricky. And for example, when you are dealing with process safety systems, it's very important to know your inventory, meaning how much you have inside your tank. At the moment, our program just works with Peng-Robinson equation of state, which is known to give poor density, liquid density prediction. So this is a limitation, because by doing that, then we made a mistake about the amounts that are present within the system. So this is one point that needs improvement, but it doesn't only affect there, because if, for instance, if you use the paracore equation, it depends on the fourth power of density. So your error in density is magnified to the power 4, and then it causes a tremendous error. And this is something that is in our to-do list for the process safety simulator, at least to change from Peng-Robinson to Peng-Robinson volume translation, because of the issue of having the right amount, of calculating the right amount, or a better estimate of the amount of liquid that you have inside your leaking vessel. So this is for one, and then the other is because of the surface tension calculation, because it's so sensitive to the density value. And we kind of learned this is kind of obvious, but sometimes you have to do the calculation first to think about it later. So the student who was doing this, he came with the results, and so there was a very big deviation. And then we thought, okay, let's put the experimental liquid density. I think it was for acetone. Let's put the experimental, then the results are much better. So it was definitely an issue with the volume, the molar volume, or the molar density estimate from the equation of state. But yeah, so but this is the issue. Again, this is in a way brings back the first question by Yanis, that had to do with what you can accomplish with one type of program and what we can accomplish with another one. And this also relates to the model requirements. If you are doing something that depends intrinsically, the quality of your result depends so much on your density estimate, as, for example, surface tension of paracore model, then you need to invest time and energy into putting, using the right model, developing the program and inserting the right model, because your simulation may be off by a lot if you don't do it. And this is, again, this is our to-do list. As the student finished, this was one of the recommendations of his thesis, and actually have the version of Penrose volume translation ready for inclusion in the process safety simulator. We haven't done it yet, but the program is ready. It's a matter of inserting it, plugging it into the simulator.
Thank you. So one final question is, in the case of surface tension, it is not only composition and pressure and temperature, although shape factor seems to be very important, like Tolman's correction. I'm making some consulting calculations. Tolman and Lorentz correction, the shape of the bubble seems to have a tremendous effect, whether it's spherical or not. That variation is much more than the variation in pressure sometimes. So I was wondering how you go about doing that, the safety problems. Did you worry about the shape of the bubble?
Not yet, Braja, but you kind of nailing as usual. You have tremendous insight into everything. And so what happened? Why I say these results are preliminary? They are preliminary because these Dyer's correlations that we implemented, they are very coarse. They are not, so they classify the type of flow and bubbly, churny, turbulent, and then you have a set of correlations that just apply. If you have this, do this. If you have that, do that. And these turned out to be, first, they are algebraic equations. And the moment so if you use these correlations, and let's say you have liquid swell and the swollen liquid reaches the exit point, the exit of the relief valve, then the moment you do that, then the conditions change and the liquid decreases, and then it increases again and decreases, and you have like a fluctuating behavior. This fluctuation behavior has nothing to do with the physics of the problem. Absolutely nothing. It has to do with the step size of your integrator, because the way it was modeled was not correct. It was not sufficient. We need to do better. We need to add this to the set of differential equations, not done as a on-off switch between different algebraic equations. This will not go any further. We have understood that, so we can do a kind of decent job at this very coarse level, but we need to go much deeper into this question. So if maybe I could ask you for a meeting so that you explain this more to me, so what you have learned, because this is something that we'd like to go much deeper. We have realized that what we have done is definitely not enough. We need to do much better on this. We are just kind of collecting the literature and trying to make sense of it in such a way that we have something that is not much more complicated than the simulation what we are doing. We do not want to kind of multiply the complexity of the simulation we are doing by 2 or 3 times of magnitude in terms of computation time. We want to have kind of something that's simple, relatively simple, but still captures the physics. But we know that what we have done is far from enough. So this is one of the reasons I didn't boast about this result, because I know it's not good enough.
Thank you very much, Marcelo. Maybe we should talk about sometime later about the thesis you are mentioning.
Yeah, definitely. I'll be glad to.
Thank you very much. So good to see you.
So good to see you too.
Would anyone else would like to ask a question?
I just want to add some comments to Marcelo's.
Please go ahead, Professor.
Yeah. So first, congratulations, Marcelo, for your very, very nice talk with a lot of job have done in these 20 more years. Very nice. My comments with regard to the question made by Professor Johannes regarding to how the process simulators do the dynamic simulation. That what I can comment about what you are doing about this dynamic simulation. You have phase equilibrium, you have constraint on volumes like vessels and other equipment with constraints on volume. One that works quite well for us doing the dynamic simulation for that, assuming that you have a good and consistent initial condition, that this comes from, for example, some steady state simulation, and you do all these equilibrium calculations, is just apply the equilibrium condition, the equality of gaseous and thermal and mechanical equilibrium, and do the dynamic simulation, because you already have the dynamic path, and these conditions are quickly satisfied by the thermodynamic model and so on. So you do not use some routines to do flash calculation, for instance. You just put as algebraic constraint and dynamic equilibrium conditions, equality, for example. And it's worked quite well for the dynamic simulation.
Yeah, equation-oriented approach,
yes,
right?
equation-oriented, yeah, exactly. So in this, actually, there is limitation for that. You have to impose the number of phases a priori. So you have that fixed size problem to solve, and there are a number of equations. But actually, if you have during the simulation, the number of phases will change, so you have to change the procedure to do something else. Okay, but this is the limitation.
Yeah, I always like this this thing about phase equilibrium calculations, because this is a type of problem in which the system of equations that you need to solve may change during the course of the iterations. So you're not only iterating on the values, you're iterating also on the system of equations that you have to solve. So this is a kind of I wouldn't know whether it's unique, but it is kind of very interesting that the system of equation will change during the course of the iterations.
Yeah, how to put everything together, and this procedure that I have showed with changing the number of phases, increasing the number of phases, reducing the number of phases, how you put all the things together, the process simulator. I think it's still an open question to do this quite efficiently.
Yeah. Now, yeah, sometimes people discuss a lot about the best algorithm to minimize the Helmholtz energy or minimize the Gibbs energy, and these things are important. Yeah, I agree. But to me, the key element is the phase stability test, because this is what will tell you whether the number of phases you have assumed is right or wrong. Without this information, if you're not sure about it, you cannot be sure about your solution. So the phase stability test is just one element of the entire solution procedure. But if I had, say, to pinpoint the crucial one, I would pinpoint this, assuming that, of course, you do not make mistake doing the other one. But the other problem is somehow easier than the phase stability test. This is the one in which you cannot fail.
Mm-hmm.
Anyone else would like to ask a question?
I think it's time to close it.
Yeah, okay. We can wrap it up then. Once again, thank you so much, Professor Castier, for your presentation.